Okay, we are recording, so that's good. And share my screen. Good. So far, so good. Let's get this over here. Open up the chat. I'm getting better at keeping an eye on it. All right. I'm not on mute. Pretty good. Okay. We're off to the races. So I guess I should show you where I got it from. Just this morning, I kind of flip-flopped back and forth on how to do this background section, I should say. So on your Moodle, I posted a PDF called Fundamentals Part 1. So we're going to work through that. Hopefully all of it, probably won't get through all of it today, but that's okay. So what I want to do, so you can just kind of download that and have it. But that's what I'm looking at here. So here I'll write fundamentals. Oh, nice and slow. Okay. Fundamentals Part 1. And I'm shamelessly stealing from another textbook that I've used, so, and that I am using for the pre-calculus course that I'm teaching. So, and because it's all the same, I figured save myself some work. Fundamentals. Whatever. So what I want to do is I just want to spend time probably spilling into next week, just working on the basics, right? So working on the fundamentals, everything that you are already expected to know. So if it feels easy, then that's a good thing, right? It's not supposed to be new. It's supposed to be kind of known to you. But depending on kind of where you're at with your schooling, maybe it's been a while, maybe it's been a long summer, I don't know. So I just want to brush up on all those things so that we're all up to snuff. Hey, my iPad just crashed. But it's still sharing its screen somehow. So I'm not sure. Okay. Or was it Notability that crashed? Notability. Might have to switch to OneNote. The only reason I'm not on OneNote is because my password is giving me grief. And I like Notability. There's some echo. Let's see here. Participants. Hey Ash, I'm gonna mute you, okay?
Yep.
Awesome. All right. Brave to not be on mute. Okay, so I want to spend quite a bit of time, and like I said, if it feels boring and just kind of slow, then that's a good thing. Then you're in a good place. But if there is anything that you feel like you need to brush up on, then this should kind of highlight it for you. Okay. So the section numbers, I mean, we can call them kind of 0.1 if we want. Like I said, I stole it from a different course, so, because we'll have a new chapter 1 from our actual textbook. But this stuff is not in the textbook, so Here we go. All right, so we're gonna start from pretty well the beginning, right? And so we're gonna start talking about just different kinds of numbers that we can have, how do numbers behave, how does math work essentially. And so if we start to think about all the different numbers that we can think of, right? So if we have some sort of number line, and I'll just write on this page, so if we have some sort of number line, let's say from negative infinity to positive infinity, somewhere here in the middle is 0, right? This would be the set of real numbers. So any number that you can put on this number line is the set of real numbers, okay? And so this is the real number line. Okay. And so what it says here is that all the numbers, any number that you can think of, right, will be part of the real number system. And so the set of real, oh, that's supposed to be a fancy R. So it's a capital R with a double back. So just kind of like, oh, like that. So fancy R is the set of real numbers. Okay. So that one's going to be important to kind of keep track of, but the set of real numbers is just all the numbers that we know. Okay. There are some other sets. There's the set of natural numbers, and so a set is just a collection of things, right? And so where a set is a collection of, and inside the set we call them elements. And we'll talk a little bit more about elements and sets in a bit here, but we're just introducing these basic sets for now. So these real numbers, they've been classified into natural numbers. So the natural numbers, also we can think of them as the counting numbers. So 1, 2, 3, 4, 5, 6, 7, right? And so these are the counting numbers. Oh, I can make it a little bit thinner here because I zoomed in. The counting numbers. Yeah. I guess there's some debate. Is 0 a natural number, yes or no? We'll say it's not. If you include it, that's totally fine. But just knowing that the natural numbers is just your counting numbers. Oh, iPad's updating, man, oh man. Right, then if I say, okay, pull a number from the set of natural numbers, then you know that I'm pulling from 1, 2, 3, 4, 5, 6, and all the way up to positive infinity, right? The set of integers does the same thing, but also goes into the negatives, including the 0, right? And so if we have to write these kind of, our fancy n has a double middle, I guess. And then our set of integers, I just write like that. Hey, maybe I don't. Just like that. Okay. Because sometimes it's hard to see how to draw these by hand instead of, but they're very similar to what's been typed out. Okay. Maybe what I'll do is, so I need some more room here. I'm gonna add a page here. There. I'll take this to the bottom here. kind of a lessons learned day, I guess. I'll make sure there's room for the next couple of notes here. I just decided to grab these, so here we go. So we can talk about rational numbers. Rational numbers are fractions, right? So they're ratios of integers, like m over n, and we like to use these letters, right, to denote just a placeholder for a number, right? And so we'll get very used to using letters instead of numbers because it's more general, right? And so it does mean that I have to define what m and n look like, but a ratio, oops, I do like it thicker though when I'm zoomed out. Or a rational number R equals m over n, where m and n are integers, right? So then we have to think back, okay, what's an integer? It can be any number, any whole number from negative infinity to positive infinity, right, including 0. But we can't divide by 0, right? So that's one thing that you need to keep in mind always, right, is, okay, whatever I do, I cannot divide by 0, right? And so where m and n are integers and n does not equal 0. Okay. We can never divide, oops, by 0. Saved. By 0, right? That's a really, really important rule to keep in mind, right? I never want to see you trying to divide by 0. It just doesn't happen. In fact, we rely on not being able to divide by 0 for finding domains and stuff later on in the course. So that's one thing that you need to really lock in right now, is that you cannot divide by 0. You can try it on your calculator, it'll tell you there's an error, right? So just in terms of terminology, right? A rational number, often we'll call it a fraction. So I've got a fraction. So a rational number is a fraction. And when we're talking about fractions, we're going to be talking about the numerator and the denominator, right? And so we need to kind of dust off the terminology here. So we've got the numerator on top is the numerator over the denominator. And even though my undergrad was in math, I had a heck of a time trying to remember which one's the numerator and which one's the denominator. And so the numerator is on top because it's numero uno, right? And so, and then the other one is just on the bottom, right? And so whatever you have to do to kind of remind yourself which one goes on top and which one's the bottom, right? So numero uno is on top, that's the numerator, and then the denominator is in the bottom, right? Just so that we get comfortable with using this terminology. Okay. So let's go back up here. So those are our rational numbers. So it's any ratio of integers. And we'll talk more about dealing with fractions. What can we do to manipulate fractions in a little bit here. Our last set of numbers that we're going to talk about and kind of need to know about is the set of irrational numbers. And so irrational numbers are things that can't be expressed as a fraction, right? And so things like pi, right? The constant pi, the constant e, root 2, right? And so these things are never ending, right? And so we call them irrational numbers. So irrational numbers, let's see here. Irrational numbers is a non-repeating decimal. A non-repeating decimal. So things like, we've got pi. Pi, we know, well, we don't know the end of pi, right? It just keeps going and going and going. It seems to be infinite. And so what's really important is that we use the approximately equal to, right? Pi is not equal to 3.14. Pi is approximately equal to 3.14159265. I cheated. I have it here. So 3.14159265. Although there's a song, but I don't know it. 3.14159265. Anyways. So here, right, we must use approximately equal. I'll put in brackets here, approximately equal. Oops. I'll move it to the next line. Approximately equal, right, for decimal approximations. So, whereas if you try, oh man, sorry. Okay, so a rational number, if we have a look at a rational number, right, can be summarized as a fraction of integers. Can be summarized as I'll say ratio instead, as a ratio of integers, right? So if we think about something weird like 157 over 495, if you do that on your calculator, right, 157 over 495, and if you've got this one here, or even the other one that they sell in the bookstore, that kind of silvery one, it'll always try to give you exact answers, which is really nice. But usually we like to think in terms of decimals, and so there's the there's an approximately equal to button. I don't know if you can see. Over the equal sign. So you go shift equals, and then it'll give you the decimal approximation. Or you can do the S to D button. So S to D. S being probably standard form to decimal. But anyways, there's a couple of different options. You can change it in the settings, but I actually like to have the exact answer come up. It's really luxurious. So yeah, anyways, I like it. But 157 over 495 is approximately equal to 0.3171717 1717, right? And so here we've come across a repeating decimal. Repeating And so what we would say is that it's equal to, now because I'm going to say that it's repeating, I can say it's equal to, I'm not going to be terribly picky about the approximately equal versus the equal, but it is something to kind of get used to thinking about. So it's approximately equal to 3.17, and then with the bar over the 1 and the 7, because that's what's repeating, right? So you want to be really clear about what's repeating and what's not. And so the repeating is just that bar, right? Or as long as I say approximately equal to, it's approximately equal to 3.17 period, right? Not exactly, because it's 3.17 repeating, right? But as long as I say it's approximately equal to, then you're good. Yeah? So just little nitpicky things to keep track of, right? Equals, approximately equal to, and sometimes even, I mean, I get lazy and I'll just do the equal to, but I try to keep track of it. In fact, I'm looking at this first one, this little guy here, and I'm thinking I could get away with an equal sign, but it's okay. Approximately equal is always technically true, so no worries. Okay, so checking for questions here, but I don't see any. Everyone's just getting warmed up for some math theory. Okay, so just as a refresher, right, we're going to talk about the properties of real numbers. Basically, how does math work, right? What are the rules? We need to know the rules to play the game. And so we've got some pretty basic things, like we've got the, I always have a hard time saying it, commutative properties, right? Which means that the order doesn't matter, right? Whether we're adding A plus B is the same as B plus A, that's fine, right? Even multiplying A times B is the same as B times A. Okay, so those are the commutative properties. Those, I think, for most of us are just kind of second nature by now, right, in our math journey. So, yeah, the commutative properties are kind of basic. Even things like the associative properties, even if we've got brackets, right? So remember BEDMAS, brackets, exponents, division, multiplication, addition, subtraction, right? And so if we've got brackets, we deal with those first. But in fact, if we're, oh, how did you know that it would result in a repeating? Because I tried it beforehand. But also because it can be expressed as a ratio of integers. Right? And so you can try other things like 49 divided by 5. Just gives me a nice decimal, 9.8, but I wanted a repeating one, so I had to go hunt it down. But so I didn't know that it would result in a repeating rational ratio, but I picked one that would. So, tricks of the trade. Oh yeah, so the associative properties just say that if we're adding and only adding, then the order that we add things in doesn't matter, right? So we can put the brackets around A plus B, or we can put the brackets around B plus C, and it doesn't matter. And so same thing with the multiplication, right? If we've got A times B times C, when you say it, it doesn't, but when you visualize it with the brackets around the A and B, it's the same as A times B times C, right? And so these first 4 properties, I would say, should be pretty second nature by now, right? So if we're adding or if we're multiplying, the order doesn't matter, right? As long as we're only adding or only multiplying, right? If we're doing a combination, then we have to be careful, right? Then bed mass is king of the jungle here. I'll do bed mass on the side just as a little. I know there are some other ones, but I think bed mass is the one that people are most familiar with. So we deal with brackets first, then exponents. Oops. Then division and multiplication. These two are actually on the same level, so you just do them in the order they appear. Same thing with addition and subtraction. Oops. And subtraction. Right, they're on the same level, I would think of them as. So you deal with your brackets first, then your exponents, division and multiplication as they appear, addition and subtraction as they appear, right? But in that order. Okay. So getting into kind of a little bit of real math here, the distributive property says that, okay, if I've got a combination of multiplication and addition, all right, I've got A on the outside multiplying, right? Because then if it's outside the brackets, we're multiplying. So A times B plus C is the same thing as bringing that A inside of the brackets, right? And so we've got A times B plus C is the same thing as A times B plus A times C. Right? So here we're expanding, right? If we were to shrink it back down, then we would be factoring. And we'll talk more about that later. Not today. Okay, so same idea. If we've got something like B plus C and then all times A, right? That's going to be the same thing as A times B plus A times C. So whichever is easiest. If it's easier to add these two up and then multiply, that's fine, right? Or if it's easier to just bring the A inside and kind of expand it, then that's fine too. They're equivalent. Okay, so we need to talk about negatives, how negatives behave. Subtracting is really just addition with negatives, right? So that's why we only have these rules in terms of addition and multiplication, because division is essentially multiplication by a fraction, right? And so so we only need rules for addition and multiplication, because then subtraction is a special case of addition and division is a special case of multiplication. So if you've got A times -1, right? So looking at this first property here, then we all know you get -A. Right? If you take the negative of a negative, you get the positive, right? And so we can use that again, right? So if we've got -A times B is the same as A times -B, so it doesn't matter which of these two is negative, as long as there's one negative, then the result will be negative. If you're multiplying two negatives, you get a positive. Right? And if you have a negative on the outside of the brackets, then you have to bring it inside, right? And so what we do here, really kind of jotted all over these things. So if you have negative a plus b, you can think of it as -1 times a plus b if it helps, not if it doesn't help, right? But this negative gets brought inside. So you get negative a, technically plus, right? Because you've got a plus b, so then plus, and then you've got negative b, right? So that's how these things behave, right? So now you've got negative a minus b, right? Because subtraction is just adding a negative number, right? So you get negative a minus b. Usually we're going the other way from here, right? Where we want to pull out a negative out front and just have one negative and some positive value in the middle here, but we need to be able to go back and forth. Same thing if we look at the negative of a minus b. Well, that's going to be, so you're going to bring the negative onto the a. Sorry, why did you get rid of the plus? Oh, because plus a negative number just makes it subtraction, right? And so if you have plus, okay, get solved. But yeah, that's just something that we're gonna use. So now if we've got the negative and then a minus b inside, right, then we've got negative a, fine. And then I'm going to keep the minus here, minus b. And then same thing, I'm going to have minus negative b. Right? And then if I look at this property here, negative of negative a is just a. So negative of negative b is just b. So here, I'm going to have negative a plus b, which they've rewritten as b minus a. And that's just because often we like to have just the positive value and then minus a number because it's easier to think about. But it actually doesn't matter. Right? So the order doesn't matter as long as the a stays negative, right, and the b stays positive. So, which is the same as b minus a. Good. So just some things to keep in mind, especially about negatives. Let's talk about fractions here. I'm going to make a copy of this and add a page. And then before I forget, okay, because I moved it up here so we can talk about all these fractions. Okay. Actually, before we do, how about we do some examples first? And page. let's start with 5x plus 1 times 3. Right? And so I'll try to make my x kind of a little bit curly. Sometimes I know people like to use just an x as a multiplier. I'll either not have a multiplier, right? If I put two things together, then they're multiplying, or I'll use the dot. Sometimes I'll use the x, but that's why I like to, if it's a math x, right? If it's a variable, then I'll make it kind of curvy. So, like that. It's just good to know. So all these rules still apply, right? Even though we've got some numbers and some variables, right? Or one variable. Right. X is a variable because we can put anything we want into x and it'll still be true. So we can still work with 5x as one unit. So this, if we expand this, right? Then we remember, okay, well, 3 multiplies the 5x. Right? So we've got, keeping the order that I've got here, I've got 5x times 3. And then plus, keep that plus there, plus 1 times 3. Right? Or for whatever reason, I always like to have just the number, so the 3 that I'm multiplying in, I like to have it on the left-hand side. So even if it doesn't come on the left-hand side, I just scoot it over, right? Because if you think of 5x plus 1 as one thing, right, as A, for example, then 3 would be your B, right? A times B is the same as B times A, right? So I can switch these around. Or I can do 3 times 5x plus 3 times 1. And that to me just feels more natural. But they're equivalent. 3 times 5x is 15x, right? So the coefficients, we can just multiply. Plus 3 times 1 puts me at 3. How about write 3 times x plus y, and I'll give you another one too to practice, and 3a times b plus c minus 2d without parentheses. So without brackets. Let you have a little stab at it. While you do that, I'll get started on the 3x plus y. 3x, or 3 times x plus y, that's just going to be the very basic distributive property, right? In fact, they're both using the distributive property because we have to bring the 3 or the 3a in later. So this becomes 3x plus 3y. Right? That one should be pretty good, right? And then I kicked it up a notch with the 3a times b plus c minus 2d, right? But as long as you kind of stay the course and just bring that 3a onto each of the terms inside the brackets, then you're going to be safe. So you've got 3a times b plus c minus 2d. Okay. So first thing I'm going to do, and I can keep these, I can use as many brackets as I want in the multiplication because it's not going to hurt, right? Brackets make a difference, right? When we're just like here, right? We can't just move the brackets because the brackets are around this addition and subtraction, and then we're multiplying. But as long as we're multiplying the brackets, we can just throw as many as we want on there. So what I mean by that is I can have 3a times b plus 3a times c. And then I could do two things. I could do plus 3a times negative 2d, right? Or I can do minus 3a times 2d. I'll do the minus, but you can go either way. And I'm going to give myself a little bit more room here. So 3a plus times c minus 3a times 2d, not just d. So I'm bringing that 3a just as a whole unit inside. So now I've got 3a times b, which I can just write as 3ab. Same thing, plus 3ac. And then I've got minus, so I'll put that down, minus, and then 3a times 2d. So 3 times 2, I can sort out as 6, 6ad, because then it's just a times d. Okay. So we kind of bumped it up pretty quickly there, but it's okay. Okay. So now we can move on to the properties of fractions. So dealing with fractions, right, is usually a little bit rusty for a lot of people. So that's okay, right? But we do need to be able to deal with fractions. And there are a couple of tricks that we have up our sleeves. And the first one is that multiplying fractions is the easiest thing you can do, right? And so to multiply fractions, if you have a over b times c over d, then you just multiply across, right? So then you get a times c, oops. This is why I don't like the dot, because sometimes if I write sloppy, it makes it look like a minus. So then I'm just going to do ac, that's a times c, over bd, b times d. Okay. So here, multiply across. So multiplying fractions is the easiest thing, and usually we like to start with addition and then go to multiplication, but because multiplication is so simple, we start there for fractions. So let's talk about dividing two fractions. So if I've got a fraction over a fraction, right, this is how I usually like to do it. So then I have to flip this, the denominator, right, and then I multiply the two, right? And so in your mind, just start doing this, right? So you've got a fraction over a fraction, and then you're gonna flip the denominator, and then you're gonna multiply, right? I don't know, some teachers call it flip and kiss. That's the only thing that I've had, but there's everyone has different sayings for remembering how to do it. But so dividing fractions is gonna look like a over b, that's my first fraction. And then to indicate that I've got a fraction over a fraction, I extend my line a little bit longer. I over-exaggerated here, but just to show you that, okay, I've got a fraction over another fraction. And then I've got over c over d. B can't be 0, D can't be 0, right? As long as B is not equal to 0 and D is not equal to 0, right? Same thing across here. In fact, I'll move it up. And then it applies for all of these, right? We can't have 0 in the denominator. We should say it explicitly, but sometimes I forget right away. Okay, so I've got a over b over c over d, right? So what I'm gonna do is I'm gonna flip the denominator, right? So the denominator becomes d over c, and then I'm gonna multiply. Multiplying is easy because you just multiply across. So this becomes a over b, so I just keep that one the same, times d over c. So this, flip and multiply. Oops. And then multiplying across is just easy, because that's what we just did here. Right, so then it becomes AD times BC. Okay. So that's dividing fractions. Dividing fractions is really useful, right? Sometimes we can even make a fraction, right? And so here, I'll just make a note. Sometimes we make fractions out of even integers, right? Something like if I have -2, -2 is the same as -2 over 1, right? So sometimes it can happen that it's going to be easier to just deal with a fraction over a fraction, for example, right? And so sometimes we make fractions, but just remember that any integer over 1 is just itself, right? And so then all of a sudden we've got this fraction that we can deal with, right? So we'll see some examples of that probably later in a bit here. So that's a little trick that we have. How about if we are adding fractions, right? So adding and subtracting fractions are going to behave the same way. We need a common denominator, right? And so adding fractions we need a common denominator in order to add or subtract fractions. To add, right, because adding and subtracting is just a special case of adding. So in order to add or subtract fractions. So if you have something like a over b plus c over b, right? Then I've got this common denominator, right? So that's why we had to brush up on that terminology, numerator, denominator, right? So here I've got a common denominator. So then I'm safe to just go ahead and add across. So that's going to be a plus c over b. So it's not b plus b, it's just the common denominator. Okay. What if you don't have a common denominator? Well, then we have to make one, right? So just like sometimes we're going to end up making fractions, we can force common denominators, right? And so if we do not have a common denominator, we need to make one again, right? So the trick that we're going to use, right, is multiplying by 1, right? And so there's a couple of different ways. We can find the lowest common denominator, we can find the lowest common factor, we can factor it all kinds of ways. I like to just always use the same method for finding the common denominator. And it's not always the cleanest or the fanciest, but it always works. So that's why I like it. And that's the only way that I'll be using. And so what I do is I force the common denominator to be the first denominator times the second denominator. Okay. And so the easiest way right? Not the cleanest, but the easiest way, or even it's definitely not the fanciest way, but the easiest way to ensure we have a common denominator is to use the two denominators multiplied together as the common denominator. But I think I'm better off just showing it. So if you've got a over b plus c over d, right, then my common denominator here would be b times d. Use b times d as the common denominator. As the common denominator. Add a page here. Hey. Okay. So how am I going to do that? So this tends to kind of be a bit of a glitch for a lot of people. So just kind of make sure if you have any questions, just ask. Okay. So if we need b times d in both denominators, right? Because then as soon as we have a common denominator, then we can add these things up and we're off to the races, right? But in order to get b times d in the denominator, well, I'm gonna have to multiply this b by d and this d by b. Ugh, should have used different letters. No, it's okay, right? One thing, another trick that we have up our sleeve is that we're always allowed to multiply by 1, right? And so we can always multiply a number, right? A number or a fraction or anything, a number or fraction by 1, okay? So a lot of the time we pick convenient ones. We pick convenient ones, right? Things like a over a divided by a is 1. 4 divided by 4 is 1. B divided by b is 1, right? So I can multiply by 1 here. So I can multiply each term by 1, okay? And I'm going to pick convenient ones. So now, to get the common denominator of BD, I will multiply both terms by 1. So what's that going to look like? I've got a over b plus c over d, and I'll kind of space it out a little bit. So we said over here on the b, I need b times d, right? And so if I need b times d here, I'm going to multiply by d over d, right? If I'm multiplying fractions, right, that's the easiest thing we can do because then I can just multiply across. But just remembering that now in the numerator, right, here in the numerator, I've got a times d, right? So no, it's not a anymore, right? It's going to be a times d, but that's okay because now I've got b times d in the denominator, and that's exactly what I wanted and needed. So same thing here, right? If I need BD in the denominator, right, then I need to multiply D by B because that's what's missing. And so I've got B over B as my 1, right? B over B is 1, D over D is 1. I'm just multiplying by 1 here, nothing to see here, right? So now this becomes AD over BD plus CB over DB. BD, DB, usually I would kind of switcheroo these and just have them look like the common denominator. Right? Order doesn't matter as long as we're just multiplying. So this becomes, so now I've got that common denominator, so now I'm able to add these up. So I've got AD plus CB over BD. Okay, so let's see if we can do some examples here. So if I've got 3 over 10 plus 4 over 15, right? I'm adding fractions. I don't have a common denominator, so I need to make a common denominator first. Right? So I'm going to identify what my common denominator is. And if you're feeling confident about finding a different common denominator, that's fine, right? I just wanted to show you the most foolproof way of doing it. And that's the way that I just showed you. And so there are other ways that you can do it. But this is fine. Oops. So our common denominator is going to have to be 10 times 15, right? I've got 10 in one denominator, I've got 15 in another denominator. So what I'm going to do is I'm going to have my 3 over 10, and then I'll use a different color just to show what's going on here. And then I just look at the denominator of the other term, and I say, okay, well then I need 15 over 15 here. And then I do the same thing, so plus 4 over 15, but here instead, I look at the previous term, right? It had a denominator of 10, so now I'm gonna do times 10 over 10. Now, each of these terms are being multiplied, right? So first I'm gonna multiply and then I can add these because then I'm gonna have that common denominator. So what I get here is 3 times 15, puts me at 45, over 10 times 15, 150, right? Which is what we said our common denominator would be. Plus, and then 4 times 10 is 40, over 150 again. So now I've got this common denominator. So now I can add these up, right? 45 plus 40, 85, over that common denominator, 150. So just keep track of that common denominator just becomes the denominator, right? So you don't add those two together. It just morphs into the denominator. Oh yeah. Can you scroll up just to the letter? Is that far enough? Good. Good, good, good. Okay. Are you guys ready for a big example? I'll write it out and then I'll give you guys some time to work on it, and then we'll go through it together. Right? But this is kind of the ultimate. So if we have 2 over 5, I'm going to put it on a fresh page. 2 over 5 plus 1 over 2 divided by 1 over 10 plus 3 over 15. Okay, give that a little go. Pause this. Start recording again. Okay. So as long as we kind of slow and steady wins the race here, right? I'm going to focus on the numerator, and then I'll do the denominator kind of simultaneously. a lot of the time, right? And I'll just deal with the numerator. I'll simplify the numerator and simplify the denominator kind of alongside each other. And then I'll flip and multiply as soon as I've got kind of the simplest version on both top and bottom. So what I have here is, okay, well, I'm adding two fractions, which means that I have to have a common denominator. I don't have a common denominator in either of these, so what great practice, right? So we've got 2 over 5. To get a common denominator, I need 5 times 2, and so I'm gonna do times 2 over 2, right? And what I'm just doing is for this term, this first term, I'm looking over here and saying, okay, well, I need the 2 times 2 over here, right? And then for this next term, I'm going to look over here and say, okay, I'm going to do 5 times 5 to get that common denominator. So plus 1 over 2 times 5 over 5, like we just said. Keeping my nice long divisor. Then I have 1 over 10. And then when I look over here to the second term, the denominator is 15. So that's what I'm going to multiply by over here, right, is 15 over 15. Right? Multiplying by 1. Plus 3 over 15, and doing the same thing, but looking at the first term, I've got 10 in the denominator, so times 10 over 10. Okay, so now I need to multiply all these fractions before I can simplify this a bit. So now I've got 2 times 2 is 4 over 5 times 2, which is 10. Plus 1 times 5 is 5 over 2 times 5 is 10. Phew, I need to have that common denominator. So it's a good thing that it worked out, right? We forced it to work out, but that's the whole idea. So all over 1 times 15 is 15. Over 10 times 15 is 150. Plus 3 times 10 is 30. Divided by 15 times 10 is 150 again. So now I've got these common denominators, so I can simplify the numerator and the denominator individually. So I get 4 plus 5 over 10 is 9 over 10, divided by 15 plus 30 over 150 puts me at 45 over 150. Now I'm at that point where I've got a fraction over a fraction, right? So I'm going to take that bottom one and I'm going to flip it and multiply, right? So now I'll just make a note here that this guy is going to flip and multiply. Yeah. So the 9 over 10 stays where it is, right? But now essentially when I flip and multiply, I bring that bottom fraction up to the same level. So now times 150 over 45. Now, again, I'm just multiplying fractions, right, which I'm allowed to do. So 9 times 150 puts me at 1350 over 10 times 45 puts me at 450. And I was just going to leave it like that. I don't need you to simplify or anything like that, right? You can just leave it like this. But if you do 1350 divided by 450 in your calculator, turns out it's just 3. Right? But that's more fluky than anything else. Okay, so that's a big one. Right? But as long as you kind of just go slow and steady, you're going to be fine. Yeah? And just remember all the little tricks, right? Multiplying by 1 is going to be your best friend. We're going to do it a lot, right, to get that common denominator. Okay. Keeping an eye out for questions here, but I see none, so we'll keep going. Good. So those are the rules for just dealing with fractions, right? And we'll get really good at dealing with fractions, so don't worry. Or I guess I should say you need to be really good at dealing with fractions. So let's talk about sets and intervals. We've already talked about sets. Actually, we talked about the sets of real numbers, the set of integers, the set of natural numbers, the set of rational numbers, the set of irrational numbers. So all these are just collections of things, right? So a set is a collection of objects, and these objects are called elements. And so there's quite a bit of notation in set theory. Okay. The first one is that we always use capital letters for sets. Okay. It's not going to be a big thing for us, but it's good to know the rules of the road. I'll add a page down here. Okay. So for sets are usually denoted by capital letters. Sets are just collections of things, right? So a set can be something like the letters in the English alphabet. They can be even numbers from 0 to 20, right? It can be just a collection of things, right? And so a lot of the time in math, we talk about sets and set theory, and it's kind of the, I don't know, the most fundamental thing. Funny because we're doing fundamentals. So it's no surprise. Okay, so there is a lot of set theory. So a set is a collection of elements. And so we use just kind of this, I guess it's just a stylized epsilon, but it's like a C made to look like an E. So it's a C with a line in the middle. We use this letter to denote in the set, right? Or even, I should say, is an element in the set. Right? So if A is a set, and B, lowercase b, is an element in A is an element in the set A, we would just write, instead of writing that out all the time, right, we would write B is in the set of A. Okay. We can also do, or C, or maybe I'll do D because otherwise it looks like a lot of C's all around. D is not in the set A if you just draw a diagonal line through it. Not in the set. Right. So we just need to be able to read that kind of shorthand notation. Okay. Talking about integers, we've got the little note, right? And so we know that -3 is in the set of integers, right? And also that something like √2 is not in the set of integers, right? Integers, oh, wait, what's going on here? Integers are the whole numbers from -infinity to +infinity, right? Starting at -3, going to +3, -3, -2, -1, 0, 1, 2, 3. Right? So that's why we started and introduced those common sets of numbers, right? Because then now when I just say in the set Z, right, you know it's a set of integers and what that means, right? Okay. Yeah, keep that color. So in your notes that I gave you, often we'll list sets in curly brackets, right? And it can be like it's called the roster method, where you just tell the person that you're talking to mathematically exactly what's in the set, right? And so here, if A is the set 1, 2, 3, 4, 5, 6, so use curly brackets. Use curly brackets to denote a set. So here are all the elements in the set of A. Okay. We can list them, right? Or we could describe them, right? So here, that's what I was going to do. A list is called the roster method, right? Everyone on the roster, you just are listed, right? Or A is the set of positive integers less than 7. Oops, almost did a Z. Hey, I almost did it again. Less than 7. Okay. This would be the description method. I always prefer just the roster method if we can, right? It's not always possible, right? But those are two ways that we can describe a set. The next way, the kind of the fanciest way to describe a set is using set builder notation. So we can also describe a set using Sept builder notation. And I can't remember if it's hyphenated. Yeah. Set builder notation. I'll add another page here. We can say that A, we still use the curly bracket because it's still a set, but A is going to be all x's, oops, just a placeholder of x, and then we do a vertical bar, and we're going to read that as such that, oops, okay. And then I'll do a description, right? And so such that x is an integer, and I can add something like x is between 0 and 7. Here, what color can I use? Slightly different, right? I can give an interval like that. We haven't really talked about intervals yet. I assume that you're a little bit familiar with intervals, but we will talk about them more. Okay. And so here, set builder notation just says that A is the set of any x such that x is an integer and x is between 0 and 7, right? Not inclusive. Okay, but we will talk more about intervals and interval notation later. So we'll go back up here. Because this is exactly what I was going to write anyways. C O. Oops. Okay. There we go. So if we've got two sets, S and T, A and B, it doesn't matter what you call them, X and Y, those are some common couplets. But if S and T are sets, then their union and S, and this is a cup, right? Or a union, a U, which you can read as or. Right? So the union of S union T, right? So S union T is the set that consists of all elements that are in S or T or in both. Okay? So a lot of the time we'll use Venn diagrams to show what sets look like. So we often use Venn diagrams to illustrate sets and their relationship. So if we have kind of, we're not going to get into it, but this is the universal set. So this is everything that you could possibly have. And in here, we've got the set S, and we've got the set T, right? And there can be some overlap, right? And so S or T is going to be everything in S, or anything in T. So the or is going to be everything that's in S or T or both. So that's the union. If we talk about the intersection of two sets, well, the intersection is just exactly what it's called, right? It's only the overlap. Okay? So the intersection of S and T is the set S, and this is a cap, so we've got a cup and a cap. And you can read this as and. And how I remember to keep them kind of separate, or at least when I had to try to remember, is, okay, so you've got this cap, the intersection, and if you just draw a little line here, you've got an A, and then it takes me to and, right? And so that's how I remember it, right? And so when I'm reading this S intersection, but really what I'm going to be saying is S and T consists of all elements that are in both S and T, so only elements that are in S and T. So as far as the intersection goes, on my Venn diagram, I've got S, oops, S and T, S and T, is just going to be this little region. And then the empty set is a special set that has no elements, okay? One thing that I will say is that, so here, the empty set is the set that contains no element. Notice that the empty set is just a 0 with a diagonal line through it. Right, and so the empty set has no elements. Right. So we can write, that's the one I'm gonna use most of the time, or we can actually show an empty set. I don't like this one as much, but sometimes it's nice to be able to show that it's an empty set with no elements, okay? But here, just kind of caution, the empty set is very different from 0. So if for some reason this is how you write your zeros, this is how my mom writes her zeros. And so that's why I'm bringing it up, because I know that it happens that people write their zeros with the line through. But from here on out in math, the 0 with a line through means the empty set, which is not 0. Right? So the empty set is a set with no elements versus 0. 0 is just a number, so it is an element. Set with no elements versus 0, an element. Right? It's not a set, but it is an element. Okay. I can even say an element of the set of real numbers. Or, to bust out our fancy notation, 0 is in the set of real numbers. Okay, so the empty set and 0 are completely different. They're not even related a little bit. Okay, where was that? I'm going to do the same thing here. Copy and sure. So there are times when we need to talk about intervals, right? Maybe we're not just talking about integers anymore. Maybe we're talking about any number between 1 and 2, for example. Even if we have such a short interval, right? Any number between 1 and 2, there's actually infinitely many numbers in between 1 and 2, right? It just depends on how many decimals you go to, right? And so that's kind of hard to wrap your head around, but that's when we're going to need intervals, right? And so intervals are just line segments, right? And so intervals are line segments. So if we have something like this, if we've got a line, and I use the arrows to indicate that it keeps going and going, and if I've got A and B here, right, then the interval between A and B, right, is going to be everything in here. Now, depending on if we want to include A and B, right, then we've got some different notation for that. Right, and so if we want to include A, we do a filled in dot. Includes A. Whereas if we do an open dot, it goes infinitely close to B, right? But it doesn't actually hit B, right? So it excludes B. And so if we want to include A, then what we do is we have our interval from A to B. So what we do is we just have A comma B. So A to B is how we read it. And then the brackets, whether we use round brackets or square brackets, that's going to indicate inclusive or exclusive. So in this case, if we want to include A, then we use a square bracket. And then if we want to go all the way up to B, but just infinitely close, but not exactly B, right? Then we use a round bracket. And we can use a combination of these things. And we can also write them using set builder notation, right? And so here, round brackets around A to B, means that X is any X between A and B, not inclusive. Not inclusive of A and B. Right? Because you don't have that less than or equal to, you just have the less than sign, whereas the only difference here is that it is inclusive of A and B. So you've got your less than or equal to. So this is your less than. And I don't know, I always had a hard time. Makes it seem like I had a hard time, but I was never like just really good at math. I just really liked math. I liked the puzzles. I liked working on math. And then you just end up with a math degree. So, but I did kind of struggle with some of these things. They didn't come naturally to me. So I had to remember all these things using little tricks. And so the less than, the alligator eating the bigger number never made sense to me, because the alligator, anyways, I'm not going to confuse you with my confusion, but then someone told me, okay, well, what if you hold up your hand? So it won't work in the screen here, but if you hold up your hand, just kind of do the loser sign, right? Then that's going to make an L on your page too, right? And so if you've got A is less than B, right, you can just read it as it comes, right? So this would be A is less than B. Okay, so because you'll want to keep track of these things, right? Less than or equal to, less than or equal to, that's the same as that inclusive. So here, this is not inclusive. And then, of course, once you've got a handle on the less than, then the opposite is just the greater than, right? So greater than, and then the greater than or equal to is, again, the inclusive version. Greater than or equal to. So these are inequalities. So I'll put that label up top here, inequalities. Inequalities. Okay. How about just as a, how am I doing? Let's do an example. Got one from the previous thing that we did. So how about we start there? So, and then we'll come back to these intervals and inequalities. If A is the set of numbers, the counting numbers 1 through 7, 1, 2, 3, 4, 5, 6, and 7, my right curly bracket never looks good, but that's okay. Hopefully the context tells you that it's the end of the set. And B is the set of even numbers 2, 4, 6, and 8. And then C is going to be the set of 7, 8, 9, 10. 7, 8, 9, and 10. Okay. Like I said, I should have squeezed in this example earlier, but I forgot. So we want to find A union B, A and B, and then A and B and C. So we can extend it to 3 sets. That's fine. Got something in my eye. But now for that third one, right, it has to have all the elements that are in all of these sets, A, B, and C. So keeping in mind that this you read as OR, so the U is OR, and basically the upside down U, or the A, I like to think of it as, is your AND. Okay. So if it has to be in A or B, then we're not picky. Then 1 is in A, so it goes in the set. 2 is in A and B, so it's definitely in the set, but we only list it once. 3 is in there, so we'll put that in our set. 4 is in there twice, so it's definitely in there. 5, 6 is in there twice, 7, and then the new one from B is 8. If we're talking about A and B, then the elements have to be in both A and B. So we found 2 was in A and B, 4 was in A and B, and 6 was in A and B. So the set is quite a bit smaller. It's just 2, 4, and 6. So now I know what elements are in A and B, but now I need it to be in A and B and C. So now I'm going to try to find overlap with C with that new set that I just found, but there are none. So there would be no elements in this set, which we indicate with the empty set. Okay. And I know I'm out of time, so we'll start back up with the intervals and the interval example next day on Thursday. Just as a heads up, I don't think that I'll be late, but I have to drop my car off at the shop, so I should be home in time. And any homework? No homework, but have a read through the notes that we're going through here. I'll redo them so that there's more space for us to work in, right? It was kind of hodgepodge today, so but that's okay. I'll kind of give us more space. So no homework, but just have a read through the rest of those notes that I posted. We'll finish them. Oh, this is not Math 120. I'm finishing Math 128, but welcome. All right, so just so there's no confusion, I'm gonna close the whole meeting and Vaughn, you'll have to join back in. Otherwise, it'll be a mess. All right, so see you guys on Thursday. And I'll try to be there on time. Bye, guys.